In this unit, we'll talk about atomic mass in ions. The atomic mass is a measurement of the mass a particular atom has, and we measure the mass of atoms in terms of atomic mass units. Officially, one atomic mass unit is defined to be 1/12 the mass of the carbon-12 atom. And this is important for us to note that it's the carbon-12 atom because we know carbon has a number of different isotopes. So carbon-12 refers to a carbon with 6 protons, which by definition makes it a carbon atom, and then another 6 neutrons rounding out the overall mass of that particular isotope. Sometimes you'll see atomic mass referred to as Daltons, often in biochemistry, and it's used to report high molecular weight or high mass compounds. When we look at elements on the periodic table, we'll see 3 things on every periodic table, and you may see more things, but every periodic table is guaranteed to have at least the atomic number, which is the number that appears above the symbol of the element itself, and then the atomic weight. The atomic number refers to the number of protons that particular element has. The symbol may or may not reflect the name of the element. So carbon, for example, the element is C. And that kind of makes sense to us because carbon, the word carbon starts with C. So it makes sense that we have C representing carbon. The first letter in an element when we write the symbol is always capitalized. And the second is always lowercase. Because we'll see with a few elements on the periodic table, it would be possible to get confused if we only used uppercase or only lowercase and not a combination of both. So the first part of the symbol is always uppercase, and then if a second letter is needed, we have lowercase. Now, carbon has the symbol C. We can see copper here has Cu for the particular symbol. So again, capital C, lowercase u. And we wouldn't want to write capital C, capital U, because capital U refers to uranium down here. And so we're always being consistent and we're being anal retentive when we write the symbol, always uppercase and lowercase. Now the periodic table has 3 types of elements in it. We have our metals, we have our metalloids, and we have our nonmetals. And what you see here is that the majority of the elements in the universe are metals. We have by far more metals on the periodic table than nonmetals or things that aren't metal. So hydrogen is a nonmetal. Carbon, nitrogen, oxygen, fluorine, these are all nonmetals. So nonmetals tend to occupy this area over here of the periodic table, and we have the metals represent everything basically to the left of that. Now between the metals and the nonmetals on the periodic table, we have these metalloids or semimetals. And these are things that have properties of both metals and nonmetals. And you'll want to go into your textbook and just review what the properties and differences are between metals and nonmetals, and know that metalloids fall somewhere in between those 2 properties for metals and nonmetals. So we have the periodic table, we've got our symbols, and I think I forgot to mention that some symbols make sense, like carbon, C, aluminum, Al, but then we get to something like iron, Fe. Well, iron isn't spelled with Fe last time I checked, so why does it have the symbol Fe? Well, it comes from the Greek. Turns out iron was known as an element for a long time, all the way back to the Greeks. And Greeks used to make swords out of iron. And so a sword in Greek was referred to as a pharos, and so we have iron swords coming from the Greek name. Now, we said we have the atomic mass, but we also have something called atomic weight, and there's a subtle difference between the 2. When we talk about atomic mass, we're talking about the total mass of protons and neutrons in an individual atom or isotope. So it only reflects one very specific atom. when we talk about atomic weight, we're talking about the average mass of all naturally occurring isotopes of that element. What you see on the periodic table at the bottom is the atomic weight, the natural abundance of all naturally occurring isotopes. And it's important to note that it's all naturally occurring stable isotopes. Some isotopes are not stable, meaning they're radioactive, and they won't be around in 10 years, 100 years, a million years. And so when we work with chemistry, we want to be able to represent the material that's going to be around on an indefinite time scale. So it's going to be around forever. So we need to know the natural abundance of each isotope. Well, how do we do that? Well, we take a lot of samples and then we use something known as a mass spectrometer. A mass spectrometer has been around for about 100 years, and it's really a great device for helping chemists and biologists identify molecules. And the way it works is we inject a sample of something, and so in this case we're going to look for the isotopes of chlorine. So we'll inject some chlorine gas into our chamber here, and then what we'll do is we will cause the chlorine molecule to break apart into chlorine atoms. And by separating the two atoms, what we can do is then accelerate these atoms through a series of plates, because when we break the bond between chlorine atoms, we create ions, which are charged particles. And so we can use potential fields to accelerate these ions down a beam and then have a slight deflection or a slight bend in our beam. And so a particular mass will travel on a certain trajectory based off of how strong the field is and what the mass of the particular atom is. And so what we can do is we can actually measure the individual masses of atoms and what their natural abundance is in samples. So this was first pioneered in 1919 by a scientist named Francis William Aston. He used the mass spectrometer to report the isotopic composition of chlorine, bromine, and krypton. So we can get the natural abundance of atoms' isotopes using mass spectrometry. Now I'm going to divert here for a little bit and talk a little bit more about these ions that we created. So in chemistry, we can have atoms that have charges. Sometimes they have positive charges, sometimes they have negative charges. So how do we know what an ion is? Well, the first thing to remember, if you have an ion of an atom, regardless of whether it's neutral, positively charged, or negatively charged, it's always going to have the number of protons that is assigned its atomic mass. So if it's a carbon atom, whether it's a positively charged atom, negatively charged atom, it always has 6 protons. The number of protons when you form ions does not change. The number of neutrons you have when you form an ion does not change. Only the number of electrons changes when you have an ion form. So the way we form negatively charged ions is by adding electrons to a neutral element. The more electrons it gets, the more negatively charged it becomes. If you have a neutral atom, then you have equal number of protons and electrons. And if you have a positively charged atom, known as a cation, then you have fewer electrons than protons, resulting in an overall charge that's positive. So what we find is that electrons are the currency in which chemical reactions take place. So what we've got here is a little practice exercise for you. And what you can do is just pause the video for a few minutes and try and figure out what the name, the atomic symbol, the number of protons are for each one of these lines and whether it forms a cation or an anion. I didn't include any neutral elements under the type of ion, so it's either cation or anion. But see if you can figure out what the rest of it is. Now before you get started, I just want to know that if you have a charge on an atom, or I should say a charge on an ion, we always write that charge in the upper right-hand corner after the symbol of the element. So if it's positive or negative 1, we just put a plus or minus. Otherwise, if it's got more than a charge, or a charge greater than 1, or less than negative 1, then what we have to do is write +2, +3, +4. So go ahead and pause the video. I'll come back and show you the results. Here's the results you should have gotten by filling out the table. So how'd you do? If you didn't get all of them, that's okay. Practice makes perfect. And if you're having trouble or struggling with this, feel free to stop by during office hours for assistance. Okay, so we used mass spectrometry to figure out the natural abundance of each isotope. And when we report isotopes of elements, unlike ions, we report them slightly differently. So when we talk about an isotope, we use an isotopic notation, which basically is writing the symbol of the element, and right before that symbol in the upper left-hand corner, we put a number there that represents the total number of protons and neutrons. So looking at 13C, this is read as carbon 13. 12C is read as carbon 12. The numbers 12 and 13 represent the total number of protons and neutrons. Now you might be asking, well, how do I know how many protons or neutrons something has just based off of a single number? Well, you have to recall that all carbon atoms, by definition, have 6 protons. So the rest of the mass there is made up of neutrons. So in the case of carbon 13, there are 7 neutrons, and carbon 12 has 6. When we look at the isotopic ratio, going back to our example of chlorine, what we saw is that we have chlorine 35 in a much higher abundance than chlorine 37. Yet both isotopes are present and stable in nature. And so we have to take this data and find a way of determining what the overall atomic weight would be when we have a sample of chlorine, because it's going to have a mix of both isotopes. So the way we get the atomic weight is we first sample all the isotopes out there and determine which ones are radioactive. So rather than using chlorine, I'm going to use carbon here just because it's a little easier. We know that there's carbon 11, carbon 12, carbon 13, and carbon 14. Carbon 11 and 14 are both radioactive, so we ignore them when calculating the overall atomic weight of the element carbon because they're radioactive and they're not going to be there in a certain amount of time. Then what we do is we take the mass of each individual atom and multiply it by its abundance in decimal form. So here carbon 12 makes up 98.93% of all carbon. Carbon 13 represents the other 1.07%. So changing 98% into a decimal, we get 0.9893 times the mass of the isotope, so in this case carbon 12, so 12. And then we're going to add it to the percentage of carbon 13 in decimal form times its mass. And when we do that, we find that the atomic weight for carbon is 12.01. So when you have carbon samples, what we're going to find is that when you have 1 mole of material, you're going to need 12.01 grams. So the atomic weights on the periodic table tell you the mass in grams required to have 1 mole of a particular element.